All right, let's talk about graphing rational functions. You're going to need your bright yellow Rady foldable in front of you as it walks you through what you need to do for each piece. All this Rady foldable does is it just tells you for R, this is how you find it. For the A, this is how you find it. It's a great resource for you to use to figure out what you need to know and how to find each point. Because as we go through this, what's going to be important is that you can find those 5 things, and then we're going to add something called holes in the graph, removable discontinuities, and we'll talk about those. So have that foldable in front of you. So what we're going to do is we're just going to walk through this. We're going to take our function, we're going to simplify it by factoring and writing it in its simplest form first, and then we're going to go find all those pieces, the R, the A, the T, the E, and the Y. And I'm going to try and explain it as best I can to help you understand what you're looking for, and then I'm going to show you what I expect to see on your graph. So step number 1, we're going to take our function and we're going to graph the factor. So this one, the y equals 4x minus 12 over x minus 1, that numerator will factor because there's a 4 in common. So we're going to take out the GCF of 4, which leaves me with x minus 3. And then this denominator is x minus 1. And you want it in this simplified form because it makes things so much easier for you to find every piece you need. So the R stands for roots. These are your x-intercepts, where your graph is going to cross the x-axis. To find your R, you're going to take your numerator and you're going to set it equal to 0. Well, if I take this part, the 4, and set it equal to 0, nothing happens. But if I take this x minus 3, set it equal to 0, now I can solve for x and I should get that x equals 3. So what I know is that right here where x equals 3, my graph is going to cross the x-axis. That's the first thing I'm going to put on my graph. The next thing is A, and this stands for asymptotes, and specifically it is the vertical asymptotes. It's the ones that go straight up and down. So we're going to find vertical asymptotes, and all of our rational functions that we deal with will have at least one. So our vertical asymptote, here is how we find it. If you look at your foldable, it means we're going to take the denominator, the bottom, the x minus 1, and we're going to set it equal to 0, and then we'll solve for x, and when we do, we get that x equals 1. Well, that tells me that right here, where x equals 1, you're going to have a vertical asymptote. So we're going to draw that in, and you want to draw it in as a dotted line because it's not really part of the graph, but it's an invisible line that graph is going to approach as it gets closer and closer to infinity, and so we need to have it on there so we can see where it is. But it's a dotted line because it's not actually part of the graph. If we were to graph this on our calculator, you'd never see that line. So we dot it instead. Now the T part can be the most confusing, partly because all of these words on here is just too much. So T stands for 2 things, either tangent or together. And so what this means is that your graph can be tangent at the x-intercept, which means that it is going to go to the x-axis or to the x-intercept, and it's going to bounce and turn it and change directions. It's not going to cross the x-axis. Together means that the 2 parts of the graph will go in the same direction at the vertical asymptote. They will either both increase or both decrease at the vertical asymptote. And to look for these, I'm looking for perfect squares. How do I know if I have a perfect square? Well, after I have factored and simplified, if my 2 factors that are the factors that I have in either the numerator or the denominator match, then you have a perfect square. So if you'll look at this one, my numerator, my 2 factors are 4 and x minus 3. Those don't match, which means I have no perfect square. So I do not have this part. I don't have a perfect square in the numerator, so I don't have that part. Now my denominator only has one factor, x minus 1. That's not a perfect. Since that is not a perfect square, it means that down here in the denominator, I don't have that either. So I don't have a tangent and I don't have it together, which means for my T, I have none. And a lot of the times this is what happens. The T part is, in my experience with what we've done in Algebra 2 so far, pretty rare. It's not never going to happen, but it doesn't happen a lot. Now the E, this stands for end behavior, which means what is the graph doing as it approaches infinity. This is known as our horizontal asymptote, the asymptote that goes from side to side. To find the end behavior, we have 3 options. We can have low over high, we can have high over low, or we can have the same. We can have equal coefficients. And here's how we look at this, okay? To determine what's going on, we're going to look. Our simplified version here. The numerator has an x. The denominator only has one x. these match because they're the same, x over x. So they're identical, which means they are the same. When that happens, and this is the fancy part you want to look at, this little part right here. Okay, if it's high over low, then you have no end behavior. There's not a horizontal asymptote. If what you end up with is low over high, then 0 is going to equal y, which means you're going to have y equals 0. That's your horizontal asymptote. However, if they're the same, so your numerator and your denominator, your variables match like ours do with the x over x, then we name the coefficients and write a fraction. So my coefficient for this one, the number in front of the x is the 4, and the number in front of this x is 1. So I'm going to have 4 over 1, which is just 4. So my end behavior, or my horizontal asymptote, is where y equals 4. And so right here, horizontally through y equals 4 is my horizontal asymptote. And so I'm going to draw it in again as a dotted line. And so that's what I have. Now the last part, this y-intercept. To find the y-intercept, where does this graph cross the y-axis? I'm going to plug 0 in everywhere I see an x, and then I'm just going to solve. So this becomes 4 times 0 minus 3 over 0 minus 1. And then I'm just going to do the math. Well, 0 minus 3 is negative 3. And 4 times negative 3 makes negative 12. And then 0 minus 1 is negative 1. And that simplifies down to y equals, my pen is not cooperating, y equals 12. And so way up here, I have a y-intercept at y equals 12. Now this is normally all I expect you to have on your graph. Where are your intercepts, your r and your y? Where are your asymptotes, your a and your e? If you can put those on the graph, you're doing well. You have found all the important pieces, so that's all you need. But because I have an x-intercept in this corner and a y-intercept in this corner and my coefficients matched, it sort of gives me an idea of what my graph looks like. It goes like this up here, and then it has a matching piece down here. And so that's what the graph would look like. But like I said, if all you get are the two intercepts, the r and the y, and then the a and the e, the two asymptotes drawn on your graph, that's all I'm really looking for. I want to make sure you can find those critical values and then be done. So let's do the next one. Do the same thing. We're going to factor first. So this numerator, I can take out an x, and when I do, I end up with 3x plus 1. And then down here in the denominator, that's a difference of 2 squares. So I have x plus 3 and x minus 3. So again, to find my roots, I'm going to end up with 2 this time. I have to set my numerator equal to 0, and I have two factors that both have a variable. So the first one, x equals 0. So I have an x-intercept right here where x equals 0. The next one, 3x plus 1 equals 0, and I'm going to solve that for x. So I'm going to subtract 1, and then I'm going to divide by 3, and I get that x equals negative 1/3. So my other one is very close to it right here. All right, so I have my two x-intercepts. Now let's do the a for the asymptotes. And again, I'm going to have 2 because I have two factors in the denominator. So I have x plus 3 equals 0. So x equals negative 3. So I have a vertical asymptote right here. And then the other one, I have x minus 3 equals 0, and I solve that for x. I get x equals 3. So I have another vertical asymptote over here. And then I have to look for my t. So I'm looking for matching factors in the numerator or matching factors in the denominator. Well, my numerator factors don't match. Neither do my denominator factors. So again, I have none here because I have no perfect squares. So now I have to do end behavior. To do end behavior, like I did before, we're going to compare the top and the bottom. This numerator has an x and an x, which makes x squared. This denominator has an x and an x, which is also x squared. So just like the one above, they match. So we're going to do coefficients. So these coefficients, if I were to multiply these together, x times x would be 3x squared, so that coefficient would be 3. This one, x times x would make 1x squared, so I have 3 over 1, which is just 3. So I have a horizontal asymptote where y equals 3 across right here. And so now let's find our y-intercept. We're going to make all of the x's equal 0. So I have 0 times 3 times 0 plus 1 over 0 plus 3 times 0 minus 3. Well, when I do the numerator here, it becomes 0. And then the denominator, I end up with 3 times negative 3, which is negative 9. Well, 0 over anything is just 0. So I have a y-intercept here also. So my y-intercept and my x-intercept, I have them in the same place. For this graph, if this is all that you did, I would call it done. You are finished. You have your 2 intercepts listed on there. You have all of your asymptotes drawn. You can call it a day. So now let's talk about what happens when I have a matching factor in the numerator and in the denominator, because that is something special. It's called a removable discontinuity. It means I have a hole in my graph. It means there is a spot in my graph that my graph goes right up to it and then stops, and then on the other side of it continues on, but there's a hole, and so it can't go through that spot or it would fall in and couldn't come back out. But we start this the same way. We factor. So we're going to factor this numerator, x squared minus 3x minus 4. It's just an x squared, so what I need are 2 numbers that multiply to make negative 4. Then when I add them up, make negative 3. So that's going to be 1 and negative 4. So my 2 factors are going to be x plus 1 and x minus 4. And then I have an x minus 4 in the denominator. And so hopefully you see that I have a matching factor in the numerator and in the denominator. That tells me I'm going to have a hole because these cancel each other out. My simplified function is just y equals x plus 1, which if you remember anything from Algebra 1, you should recognize that as a straight line. It's just going to be x plus 1. It makes a straight line because the x is, there's only an x. I have no fractions, no x squared. This is going to make a straight line. But first we have to find out where is the hole going to be. And I'm going to write it over here because I don't have enough space in that little bitty spot I've given myself. To find the hole, you take the factor that you canceled out. In this case, it was x minus 4, and you set it equal to 0. Well, that means x equals 4. But that's only half of it. I know that the hole is going to be somewhere where x equals 4, but I need the y value. So to get the y value, I'm going to plug it back into my simplified version. So y equals x plus 1 or 4 plus 1. So y equals 5. So where my hole is going to be at 4, 5, which if I put that up here on my graph is right here. And I'm not going to color it in. You can if you want, just make it a bigger dot than normal. But that's my hole. I leave it open because it's a hole. It should be open like that. You can see you could fall in. So there's your hole. This is the only new part. The rest of this is what we've done before. So for the r, we're going to go with simplified function. I'm going to take my numerator. Remember, this would be over 1. So my numerator would be x plus 1. Set it equal to 0. So I have an x-intercept at x equals negative 1. So I'm going to draw that in. Now for my asymptote. I have to go back to after I factored, but before I canceled stuff out to get my numerator, or denominator. My denominator was x minus 4. I set it equal to 0, and so that gives me that I have an asymptote at x equals 4. The only problem is, don't do this yet, I'm going to show you. That means that I have a vertical asymptote right here, but that is in the same place as the hole I just put in. You cannot have a hole and a vertical asymptote in the same place. The hole takes the place of the vertical asymptote. And so you're not going to draw in this vertical asymptote. What that x equals 4 tells me is that I have a discontinuity, a removable discontinuity of some type, a part in the graph where it breaks at x equals 4. But I'm not going to draw the asymptote because you don't draw an asymptote in the same place you have a hole. The hole takes the place of it. So we're good there. So now we have to look at our 2. Well, if I look at my simplified version, x plus 1, there's not even a squared anywhere, so this doesn't have a t. And then for my end behavior, anytime you have a variable and then a number, this becomes, the number that is all by itself is automatically low. So I have an x over a 1, which means this is going to be high over low. And if you look at your foldable, when it says you have high over low, it means you don't have end behavior. There's no horizontal asymptote. And there's not going to be because this graph makes a straight line. So let's find our y-intercept. Let's plug in 0. So y equals 0 plus 1, which is just 1. So I have a y-intercept right here. So now I have a straight line that goes to this hole, stops, and then continues on the other side of the hole. I hope you draw straighter lines than I do. And that's what your graph looks like. So let's do one last one just to make sure we're good with this business of a removable discontinuity and where the graph is. So step 1, we're going to factor just like we've been doing. So this has a 5 in common, so I'm going to pull out a 5, which leaves me with an x minus 3. And then I have an x minus 3 in the denominator, so you can see matching factors, cancel them out. I'm going to end up with y equals 5, which again is going to be a straight line. We've learned this in Algebra 1. It's actually going to be a horizontal line, and we'll talk about that in a minute. But here's what I have. So my whole is going to be at that factor that I just canceled out. X minus 3 equals 0, so x equals 3. And I already know from my simplified version here that y equals 5, so my whole is at 3 comma 5. So we're going to put that on our graph. 3 5, it's right here. Now we're going to find our roots and all of our stuff. Well, we'll take our numerator. Well, this is 5 over 1, so 5, set it equal to 0. Well, that doesn't make any sense, which means I don't have an x-intercept here. This graph is not going to cross the x-axis because my number that I have left is not a 0. My asymptote, we're going to go ahead and find it, but we're going to be in the same boat as we were with the last one. So I'm going to have x minus 3 is equal to 0 because that's what was in my denominator when I factored. So I get x equals 3. But that's in the same place as the whole I just drew. And remember, the whole takes the place of the asymptote. So that discontinuity is already there. There's nothing squared, so I have no 2. Now for my end behavior, all I have is a 5 over a 1, and that's it. I don't have any variables at all, which automatically is low over high, so I don't have a horizontal asymptote. And my y-intercept, well, if I plug in 0, there's nothing to plug it into. I just get that it's at y equals 5. There's my y-intercept, and so I know I have a horizontal line that goes across through here to the hole, and then on the other side continuing just like this. So that's graphing rational functions with the radii. Those are all the steps. Again, if you still have questions, bring in your foldable and your homework. We'll go over whatever we need to. I will talk to you later.